Jai Hind everyone. I am Deepak Narang, Assistant Professor in Electrical and Electronics Department of Ajay Kumar Garg Engineering College. The topic of my today's talk is temperature detectors, which is basically comprised in subject sensors and instrumentation. It's a second year subject. So temperature sensor or transducer, as we know, these sensors are widely used in industry application as well as in home appliances like refrigerator, oven, geyser, and in industry we can use them in blast furnace or to check the temperature of our weather and other applications like temperature of our um, engine in vehicles. Okay, so the basic temperature sensor which we are very well aware of is mercury based or mercury filled glass thermometer. It is having a glass which is filled with mercury in it, and it is based upon the principle of expansion. As temperature rises, mercury expands and it displaces from one point to other, and this displacement is generally calibrated in terms of temperature. So this is very common thermometer or temperature sensor which we generally use in our home for measuring body temperature, but this is not suitable for industrial application. There we need some other modified version of temperature sensors. So these temperature sensors are resistance temperature detector, which are generally termed as RTDs. Second is thermocouple. Third is thermistors. So we shall study one by one in detail what are these temperature transducer or sensors exactly are. So first of all, resistance temperature detector. The basic principle is, as its name suggests, its resistance changes with change in the temperature. So these are basically passive analog type transducers. Okay, and their resistance of conductor changes when temperature is changed, and this property is utilized for the measurement of temperature. And the relation of resistance with respect to temperature is generally governed by this equation, where R is equal to R naught 1 plus A1 into T plus A2 T square and so on, where A1, A2 are constants and T is the temperature which we actually want to measure. But this is quite complicated equation. We approximate this equation as a first order equation, where R is equal to R naught 1 plus alpha delta T, where R is the resistance of conductor at temperature T. T temperature, the temperature at which we are working, and R naught is that resistance of that conductor at some reference temperature, and that reference temperature may be our room temperature or say at 0 degree, but we generally take it as 20 degrees Celsius. Alpha is temperature coefficient of resistance, and here this is having positive temperature coefficients, because as temperature rises, resistance also rises. So RTDs are basically having this property that temperature, their resistance increases with increase in temperature, and delta T is the difference between the operating and the reference temperature. And the most commonly used metal for RTD is platinum, because it is highly stable metal which can withstand at a varying temperature range. So, what should be the basic requirement of a conductor to act as an RTD? So, first of all, obviously, the change in resistance per unit change in temperature should be as high as possible. Only then it would make that RTD highly sensitive, because our main objective is to get the change in the resistance. If temperature is increasing but we are not getting any change in resistor, there is no use of that particular metal. So that change should be as high as possible. Second is, the material should have high value of resistivity, so that with minimum volume of that material we can construct our temperature detector. And third is, there should be a linear relationship between the temperature and the resistance. It should not be non-linear. There should be continuous linearity between the resistance and the temperature. And this is basic construction, how our RTD looks like. And this is main element which comes in that contact where we want to measure the temperature. So, what are basic materials of RTDs? So, however, there are so many materials, but I have listed out only two. First is Balco. Balco is basically annealed resistance alloy with nominal composition of 70% nickel plus 30% iron. So this is composition of this Balco RTD, and it is having 500 ohm resistance at a temperature range -42 to 50 degree Celsius. But next is platinum. This is highly used sensor in industrial applications. So sometimes it is also referred as PRTDs, that is platinum resistance temperature detectors. Okay, so because this possess linear response and stable over time, it does not deteriorate very easily with the passage of time. It shows very linear and stable relationship, and it have resistance up to 100 ohm. Platinum film sensors on an insulating base provide high resistance to the tune of 1000 ohms at 74 degrees Celsius. With this high resistance, and sensor is relatively immune to self-heating process and respond quickly to changes in the temperature. So this is very simple numerical problem generally asked in examination. So a thermometer has a resistance of 150 at 20 degree centigrade. Calculate the resistance at 50 degree Celsius. So what we are given, R naught is given to us, that is 150, because this resistance is at our reference temperature, and R we are supposed to find out, and alpha, this is temperature coefficient which is given here, and delta T is temperature difference, which is 50 minus 20, that is 30. So when we put all these values, we get R is equal to approximately 167 ohm. Next, temperature sensing device is thermocouple. Again, this is very much used in industrial application where we want to measure very high range of temperature, then thermocouples are preferred over there. Thermocouple, as its name suggests, that is something coupling which are connected to each other by some thermal equation. Okay, so thermocouple is a transducer that converts thermal energy into electrical energy, and it is constructed by joining wires made from two dissimilar metal and which form a junction. So this is something like this: when two dissimilar metals are joined together, so they form two junctions, junction 1 and junction 2. This arrangement is termed as thermocouple because these two junctions are kept at different temperature, and that is why they are known as, they act as active transducers. Why active? Because thermocouple doesn't require any auxiliary power supply to convert temperature into electrical energy. Okay, so a thermocouple functioning is based upon Seebeck effect, which is very popular phenomena, which states that if two dissimilar metals are joined at a point, they will generate a small measurable voltage when the temperature of the point of connection changes, and the amount of voltage depends upon the amount of temperature change and the characteristics of metal. It means, what is Seebeck effect? When two junctions are formed by using two dissimilar metals, say A and B, and these junctions are kept at different temperatures, say this is kept at 0 degree Celsius and this is kept at, say, 150 degree Celsius. So due to difference in these two temperature, we get an EMF in outer loop of this circuit, and this effect is termed as Seebeck effect. So the magnitude of this voltage which is produced due to the temperature difference depends upon the, first of all, what kind of material we are using, and second, what is the amount of temperature difference between two junctions. The junction of two wires of the thermocouple is called the sensing junction. So here one junction becomes our sensing junction, junction 1, junction 2. If we insert this part to that surface where we want to measure the temperature, so this becomes our sensing junction, because through this junction we are measuring that temperature which we actually want to measure. And since the temperature difference between these sensing junction and the other end is critical factor, the other ends are either kept at constant reverse temperature or simply maintained at room temperature. It means if we are connecting some leads in between some these metals, so they form a different junction because they are connected, obviously they will be connected by some other material, so they will form some other junction. So to maintain its proper functioning, these junctions are also kept at room temperature. And second junction, okay, this is kept at some constant temperature. Which is not in contact with the measuring point. This junction becomes as reference junction. Okay, and its temperature is generally taken as 0 degree centigrade. Okay. However, we can use other reference temperature as well, but generally we take this temperature as 0 degrees centigrade. So we call this junction as cold junction, and this junction, which is our sensing junction, this is termed as hot junction. Okay, so cold junction generally act as our reference junction and hot junction act as sensing junction. Okay. Next. So like RTD here, this is the equation how EMF developed in thermocouple is related with the temperature difference. This is related by this equation C T1 minus T2 plus K into T1 square. This is T1 square minus T2 square. So this is the relation. This is quite non-linear relationship between temperature difference and the EMF developed in thermocouple. Okay, here C, K are constants of the thermocouple material. T1 is the temperature of hot junction and T2 is the temperature of cold or reference junction. So this is a graph of different material, like this is chromium and constantan, okay, chromel and alumel, iron and constantan, how their EMF changes with respect to temperature. As we can see, this material is showing a high range of, this produces very high output, but its temperature range is bit low, up to 1000 degree centigrade. However, we can see iridium combination shows a wide range of temperature range, but its output is very low. So we have to select the combination according to our application. Sometimes we'll requiring high temperature range, sometimes we'll be requiring high output voltage. So another example, numerical example, during experiment with a copper constantan thermocouple, it was found that C, that constant is equal to this, and K is equal to 4.50 into 10 raised to power minus 5. T1 is given to us, that is 100 degree, and T2 cold junction is taken at kept in ice, so T2 is 0 degree centigrade. Indirectly it is given 0 degree centigrade. Compute the resultant EMF induced. So by putting this, all these value in this equation, C is given to us, T1 is 100 degree, T2 is 0 degree, we get voltage as 4.20 millivolt. This is very simple numerical problem. Next is, this is complete chart of combination of different materials. This is a first wire, this is second wire, which form a thermocouple. So first is copper and second is alloy of 40% constantan. This is 40% constantan and plus 60% nickel, and some copper is added, and this form a complete thermocouple material. Its temperature range is -250 to 400 degree centigrade, and its characteristic, it can resist oxidation and reduce least effect of atmospheric condition, Second is iron and constantan combination. It can withstand or it can measure temperature range from -200 to 850 degrees centigrade. It is having low cost and least effect resistive to our moisture and oxygen. Next is chromel and chromium combination. Second is alumel, nickel and aluminium. So this even can measure temperature up to 1100 and it is also resistive to oxidation, but it is very much sensitive to or for the atmospheric condition. Okay. Likewise, we have other rare metal couple as well, like platinum, rhodium and platinum, tungsten, rhenium, tungsten, rhenium. Here, however, we are using same metals, but the composition is different. Here tungsten is 95%, here tungsten is 72%, here rhenium is 5%, this is 28%. So this is used in non-oxidizing atmospheric only, okay, and the 5% rhenium arm is brittle at room temperature. So these are various shapes of thermocouple which are used in industry, like sealed sheet, isolated, grounded, exposed and exposed bead. So what is in exposed junction? In exposed junction, conductors are outside the thermocouple. These conductors are outside the thermocouple. They have very rapid response to temperature changes but are easily damaged. Second is grounded. In grounded junction, the conductors are connected and welded to the external sheet. Here, this is not outside, rather it is welded with this external sheet. Okay. So they are not properly insulated and may be affected by EMFs. Third is ungrounded junction or insulated. In this, it uses magnesium oxide insulating material to protect the sensor from other EMFs. The response time of this ungrounded thermocouple is slower than grounded junction type. They are used to protect sensitive electronic devices from feedback voltages. Here we can list some industrial application of our thermocouple. So first is in food production. As we know, temperature is the critical parameter in food items, and to measure that temperature will be requiring some more sensitive devices like thermocouple. So thermocouple finds in its application in food industry as well. Like thermocouple are perfect for food industry because they supply accurate reading in few seconds. Food product can be checked in any phase of its production. Food production thermocouples are a two-piece unit with a handled readout, and second is this is detachable probe. So in the tip of probe there are two wires connected to each other. Flat-headed probe measure the surface temperature. Needle probe take the internal measurement and the air temperature of ovens. So by this measurement we can make the food delicious, or we can cook the food in a proper manner. Second is in furnace. This is diagram of our furnace thermocouple. Actually, how it is used over there. A pilot light is responsible for igniting the furnace. Here one pilot is given which actually ignites the furnace. But if the so what is the role of thermocouple here? Thermocouple basically shut off the gas supply when it doesn't sense a flame or prevents the furnace from receiving gas when pilot is out. It means pilot is not working but useless gas supply is there which is very harmful. So to avoid such situation, thermocouple, if thermocouple is not sensing any flame here, okay, so it shuts off the gas supply and it restricts gas from building up in the furnace, which make the system much safer. So this is how thermocouple. And next sensor is thermistor. As its name suggests, it's a combination of two terms, thermal plus resistor. It is quite similar to RTDs, but having one difference, they possess negative temperature of coefficient. Rest, their working is similar to RTD, okay, and like RTD, they are also passive analog temperature sensor. Okay, so they are composed of semiconductor material, obviously because they are having negative temperature coefficient. Only semiconductor material possess negative temperature coefficient. They are used in application which involve measurement in range of -60 degree to +15 degree centigrade, and the resistance of thermistor ranges from 0.5 to 0.75 mega ohms. Thermistor is a semiconductor which is made by sintered mixture of metallic oxide such as manganese, nickel, cobalt, copper, uranium. They possess negative temperature coefficient. Okay, that is their resistance decreases as their temperature rises. These are various shapes of thermistor. This is in form of bead, this is in form of probe, this is disc, and this is rod. So thermistors are available in these four shapes. How their resistance is related with the temperature? This is related by this formula, RT1 is equal to RT2 exponential beta 1 upon T1 minus 1 upon T2. Again, this is non-linear relationship between resistance and temperature, where T1 is the first temperature point in kelvins, T2 is second temperature point in Kelvin, R1 is the thermistor resistance at T1 temperature, R2 is resistance at T2 temperature. So based upon this equation, we can solve this numerical where it says a 10 ohm kilo NTC, that is negative temperature coefficient thermistor, has a B value of, this is actually beta 3455. So beta is given to us. Temperature range 25 to 100 degree centigrade. So R1 is 100 kilo ohm, T1 is 25 degree centigrade, T2 is 100 degree centigrade, and R2 we are supposed to find. This is supposed to find out. Okay, so by using this equation, just put all these value in this equation. Okay, we have to take natural log, this has to convert it into natural log, and by solving this equation we get Rx as 973 ohms. So what is basic characteristic of thermistor? As we can see in this diagram, as temperature is rising from 0 to 120 degree, the resistance is decreasing. So it shows that as temperature rises, resistance decreases. If we compare with respect to RTD, this is thermistor characteristic, and this is platinum, that is RTD characteristic. Temperature and resistance. So we can say as temperature is decreasing, it shows a high amount of decline in resistance as compared to platinum. Platinum is showing positive change in resistance, but change is very small. This change is approximately only this, but here the change is this much. Okay, but thermistors we generally used for lower temperature ranges. Generally it is used in electronic circuit to judge the temperature. How thermistors are basically used to measure the temperature? The simplest way is to use the thermistor as a part of potential divider. This is potential divider circuit, where this is constant resistance and second part of resistance is based upon thermistor. So here we want to measure voltage across this part because this is thermistor resistance. So V out, if we apply potential divider formula, this is RTH over RS plus RTH into total applied voltage, that is Vs. And if we say our RTH, sorry, 10 kilo ohm thermistor with a series resistance of 10 kilo ohm, if we say these two resistance are 10 kilo ohm, 10 kilo ohm, and this thermistor resistance we are considering at room temperature, we get this as 0.5 into Vs. So our V out will be equal to this 0.5 of Vs, and our Vs is equal to say 5 volt. So we shall get 2.5 volt at output. Okay, and this is taken at room temperature. If temperature further rises, obviously this resistance will get changed. Again put this resistance in this formula and we shall get the V out in this manner. So what are basic advantages of thermistor? It has high sensitivity with stable response. It is available in different small sizes, even its size may range up to some mm as well. Thermistor are very rushed and least costly. They has a wide range of resistance values. They prevent self-heating if low current is passed through the thermistor. For this we actually need to apply some temperature compensation circuit. There is no need for compensation of lead wire, fast output response, high temperature coefficient resistance. The life of thermistor is long and can withstand electrical and mechanical stresses. So this was all about the basic functioning of various temperature sensors, which are basically thermocouple, RTDs and thermistor. So thank you. Jai Hind.